Hi everyone, welcome back to Rishabh's World. I'm Rishabh and I'm 12 years old. And you're watching my new podcast segment, Exploring the Cosmic Files with Rishabh S. Ranthir. But before we start, please hit the like, subscribe, and the notification bell button so that you won't miss any of my future videos. Science, cosmology, physics, and astronomy are some of my most favorite topics. I've always been interested and intrigued with how things work in the universe. These videos are just my humble attempts to share some of the things I've learned over the past few years in a simple way with all of you. Please do like and share them. The video for today is Understanding Quantum Physics and Elementary Particles. This was a project I had made for my school last year, and I had received a lot of appreciation from my teachers and friends. I have reworked on the presentation and decided to make a video and share it with all of you. Hope you like it. I also previously uploaded another video that I made for my school's passion project. It's called Origin of Our Universe. Please do watch it as well if you haven't. I will tag it towards the end of the video. Today's topic is understanding quantum physics and elementary particles. So first, let's start off with, what is quantum physics? Well, quantum physics is the study of matter and energy at the most fundamental and simplest levels. It aims to uncover the properties and behaviors of the very building blocks of nature and everything that surrounds us. But then, what is quantum mechanics? Well, quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. All matter is made up of elementary particles. Elementary particles make up the smallest layer of physical reality. In atoms, there are electrons, protons, and neutrons. Electrons themselves are elementary particles, but protons and neutrons can be further divided into elementary particles. Protons are made up of 2 up quarks and 1 down quark, and neutrons are made up of 2 down quarks and 1 up quark. But what exactly are elementary particles, and what exactly are these quarks? Well, now let's take a closer look at these elementary particles. Now, there are 3 types of elementary particles: the quarks, the leptons, and the bosons. In this table, you can see all of the elementary particles known to man. The purple ones are the quarks. They are the up, down, charm, strange, top, and bottom. The ones with a line on top are their respective antiparticles. The ones in green are the leptons. They are the electron, muon, and tau particles. They also have their own neutrinos, the electron neutrino, muon neutrino, and tau neutrino. Again, the ones with the line on top are their respective antiparticles. But there's an exception. The electron has a plus sign instead, because the electron itself is negatively charged, so its antiparticle will be positively charged. Next, the ones in red are gauge bosons or messenger bosons. They are the gluons, photons, the Z and W bosons with the W boson's antiparticle, and the one in yellow is the Higgs boson. I have made a separate video regarding the Higgs boson and the Higgs field. I'll tag it at the end of the video. Now, all of these particles have a value, that is the charge, spin or intrinsic spin, momentum, and mass. Each particle has a different value for each of these properties. Now, measuring values like these in the quantum realm is extremely difficult because quantum information is very fragile. Measuring the quantum information changes it. Let me explain. Even though our normal physics doesn't always work in the quantum world, particles can hit one another and make each other move, just like how normal objects move in the macroverse. We see because light from the source is bouncing off an object and hitting our retinas. This impact will impart a little push to an object, and I mean very, very small. But these subatomic particles are so small that photons are just too big to collide, and they just move away and bend around the elementary particles. But we can fix this by using higher frequency photons like ultraviolet rays and gamma rays. But more the frequency, more the power, right? Now the push of a photon of a higher frequency is so great that when it collides against the particle, it will launch it away at extreme speeds, changing all the value of the information. So you cannot precisely measure the values of elementary particles all at the same time. They have to be observed individually and can change at any time. The properties or measurements of these particles will determine the quantum state identity of each particle. Next up, particle wave duality. Particle wave duality is the concept in quantum mechanics that every particle or quantum entity may be described as either a particle or a wave. During the double slit experiment, it has been observed that elementary particles like photons and electrons can behave both like particles and waves. Next up, we have the Heisenberg uncertainty principle. Heisenberg's uncertainty principle, that was created by Werner Heisenberg, a German scientist, states that it is impossible to simultaneously measure the position and the momentum of elementary particles, such as a photon or an electron, with perfect pinpoint accuracy. This principle was based on the particle wave duality of matter that we just looked at in the last slide. Next up, fields. But right before that, what are fields? Well, fields make all the elementary particles. Fields are like the oceans, and the elementary particles are disturbances and waves in the oceans. For example, light or photons are made by the electromagnetic field. There are two types of fields, matter fields and force fields. Quarks and leptons are made by matter fields, while bosons are made by force fields. But wait a minute, what are forces? Well, forces are like the rules of the universe. They tell particles how to behave and interact with each other. And there are four main types of fundamental forces: the strong nuclear force, the weak nuclear force, the electromagnetic force, and finally, the gravitational force. But don't worry, although these names sound quite complicated, they're actually very simple. You don't have to be confused. I was confused earlier as well. So let us look at these forces a little more closely. First, the strong nuclear force. The strong nuclear force binds the component particles of an atom's nucleus together. The strong force is built between the nucleons or the protons and neutrons inside the nucleus of an atom. Also, they are present in the quarks in the protons and neutrons. The strong nuclear force is also simply sometimes referred to as just the strong force or the strong interaction. It is carried by one of the bosons that we seen earlier, the gluon. Next, the weak nuclear force or the weak interaction. This force participates in nuclear fission, which happens in nuclear reactors and nuclear bombs, and also nuclear fusion, which happens in our sun. It is also responsible for nuclear beta decay and neutrino absorption and emission. It is carried by the Z and the W bosons. Next is a force that you might have known when you were around 10 years old, the electromagnetic force. This force is responsible for the atomic structures and chemical reactions. It is a type of physical interaction that occurs between electrically charged particles and is a combination of all magnetic and electrical forces. The protons use the electromagnetic force to bond with electrons, while the electrons only use the electromagnetic force to bond with the nuclei. The protons and neutrons, along with the strong nuclear force, also use the electromagnetic force to strengthen the nucleus up. That's why the nucleus is so dense, strong, and tight. The electromagnetic force can be attractive or repulsive, as you have seen in magnets. This is carried by the photon. Yes, the same photon that we use to see all the objects around us. Next is one of the most important forces at the macro level, the gravitational force. The gravitational force is a fundamental interaction which causes mutual attraction between all things with mass or even energy. Gravity is, though, by far the weakest of the four fundamental interactions, but it also has an infinite range all over the universe. The gravitational force has no significant influence, or even any influence, at the level of subatomic particles, as subatomic particles are influenced by much more stronger forces, that is the nuclear forces and the electromagnetic force. However, luckily for gravity, it is the most significant interaction between things at the macroscopic scale, because the strong nuclear force, electromagnetic force, and the weak nuclear force only help matter follow the laws of physics at the subatomic level. It determines the motions of planets, stars, galaxies, and even photons and light. Scientists theorize that it is carried by a particle called a graviton. That's it for today. I hope you enjoyed the video. Thank you for watching. Bye.